Proxima B may be the closest planet that could host life, and one of the most dangerous places for life to survive. It sits in the habitable zone of the nearest star to the Sun, but that same orbit may expose it to violent flares, radiation, and atmospheric loss. Some studies say it could still hold water, maybe even life. Others say it may already be a dead world, and that is what makes it terrifying. Proxima B is not some distant world that only matters as a data point. It is just over 4 light-years away, orbiting Proxima Centauri, the nearest star beyond the Sun. That makes it different from almost every other exoplanet people hear about. It is close enough that scientists do not only think about it as a discovery, they think about it as a future target. It is one of the first places where better telescopes may move us from "we know the planet is there" to "we can start figuring out what kind of world it really is." That is why the stakes feel bigger with this planet. It is the nearest serious test of whether a rocky world around another star could support life. The first thing that makes Proxima B sound exciting is how familiar the numbers look. Its minimum mass is a little above Earth's. That makes it sound rocky and roughly Earth-sized. It orbits in the habitable zone of its star, which is the region where liquid water could exist if the planet has the right atmosphere and pressure. Those facts are why people quickly call it Earth-like, but that label gets misleading very fast once you look more carefully. Proxima B orbits only about 7.3 million kilometers from its star, about 4.5 million miles. That is extremely close. Its year lasts just 11.2 Earth days. So yes, it is in the habitable zone, but only because Proxima Centauri is much dimmer and cooler than the Sun. To get enough energy, the planet has to stay very close. That changes the whole situation. In our solar system, a distance like that would put a planet deep in a dangerous inner orbit. Around Proxima, that same closeness is exactly why the planet is even being discussed as potentially habitable. The detail that makes it sound hopeful is also the detail that makes it risky. That is where the story becomes more serious than the headlines. The honest version is not that life has been found there. The honest version is that scientists are split between 2 very different possibilities. Some studies suggest Proxima B could keep conditions that are favourable to life if certain things go right, especially if it has enough atmosphere and maybe some form of magnetic protection. Other studies suggest the star may hit the planet with enough flares, radiation, and charged particles to strip away an Earth-like atmosphere and damage the surface badly. The nearest world that might host life may also be one of the clearest examples of how a planet loses the chance. That is why the title works without needing exaggeration. The fear is built into the structure of the system. To sit in the habitable zone of a dim red dwarf star, a planet has to orbit very close. If it orbits very close, strong tidal effects become likely. If it orbits very close to an active star, the atmosphere may take constant damage from high-energy radiation and violent stellar activity. None of those problems are separate from the habitability story, they are part of it. The same setup that creates the possibility of surface water may also create the conditions that remove it. That makes Proxima B important in a way that is bigger than one planet. If life exists there, then life did not appear under Earth-like conditions. It would have developed under a red star, in a compressed orbit with a much harsher space environment than Earth's surface life has ever had to face. That would mean life is more adaptable than many people assume, but if life does not exist there, that result is also important. Then the nearest potentially habitable rocky world, we know would already be showing us how narrow the safe range for life might be. Either answer changes how we think about habitability, and that is the first real escalation in the Proxima B story. This is not just a nearby planet that might be nice enough for liquid water. It may be a test case for whether planets around red dwarfs can actually stay habitable long enough for life to matter. Proxima B forces a harder question than most people expect, not, is the planet in the habitable zone, but can a planet survive what comes with being there? That is why Proxima B feels unsettling. It is close enough to matter right now, close enough that better observations may transform the debate within the next generation, and close enough to become the main target in the search for life beyond the solar system. But the closer scientists look, the less simple the story becomes. The nearest place that might support life may also be the nearest place showing us how easily habitability can break. And the next problem is even more serious. A lot of this danger does not come from the planet itself. It comes from the star, because Proxima Centauri is not just a smaller version of the Sun, it is a very different kind of threat. Proxima Centauri is not a smaller sun. That is where the danger gets more serious. A lot of people hear small star and assume that means a weaker, calmer version of what we know. That's the wrong way to think about this system. Proxima Centauri is a red dwarf, and that does not just make it dimmer than the Sun, it makes the whole environment around it different. Different rules, different risks, different limits on what a nearby planet can survive. Proxima Centauri has a surface temperature of about 3050 Kelvin. Its radius is only around 14% of the Sun's, and its mass is only about 12% of the Sun's. So yes, it is much smaller and much cooler than our star. In visible light, it is faint. If you only looked at brightness, you might think that means a planet near it would have an easier life. But visible brightness is not the full story. The important point is that a dim star forces a habitable zone planet to move much closer in. And once a planet moves that close, almost everything gets harder. Tides get stronger. Radiation matters more. Atmospheric survival gets harder. The distance to the star stops being a detail and starts controlling the entire story. That is why you cannot treat the star like background scenery. Proxima Centauri is not just the lamp lighting the planet. It is the system's main driver. It decides how close Proxima B has to orbit. It decides how strong the tidal effects may be. It decides how much high-energy radiation the planet receives. It decides whether the atmosphere gets time to settle or gets hit over and over again. So when people ask whether Proxima B could support life, the first serious answer is this. You do not start with the planet, you start with the star because the star sets the terms. And Proxima is not just small, it is magnetically active in a way that changes the whole picture. NASA has pointed to evidence for a roughly 7-year activity cycle in Proxima Centauri. Researchers have also found that about 1/5 of the star's surface can be covered with spots at the same time. That is an extreme level of spottedness compared with the Sun. On our star, sunspots matter, but they do not usually make people rethink whether Earth can keep its atmosphere. On Proxima, magnetic behaviour is not a side note. It is one of the main reasons scientists are cautious about habitability in the first place. That matters because star spots are not just cosmetic marks on the surface, they are signs of magnetic activity. Strong magnetism means instability, flares, changing radiation output, and a more violent space environment for any nearby planet. So when scientists describe this system as volatile, that is not dramatic wording added after the fact. It is a direct description of a star whose behaviour is measurable, recurring and strong enough to shape the long-term fate of planets around it. Then the flare problem makes everything worse, because this is not theoretical. In 2019, during a 40-hour observing campaign, astronomers saw Proxima produce its largest recorded flare. In ultraviolet light, the star briefly became about 14,000 times brighter than normal. That number is not just impressive, it is the kind of number that changes how you think about survival near the star. And it was not a one-time event in an otherwise quiet period. The same observing run caught many other flares too, large, medium, and small. That means the planet is not orbiting a star that only rarely becomes dangerous. It is orbiting a star that can shift from relatively calm to violent on very short timescales. That changes how you picture the sky above Proxima B. On Earth, life on the surface does not spend its time worrying about repeated star-driven punishment. Our atmosphere and magnetic field deal with most of that, and the Sun is much more stable from the point of view of surface biology. On Proxima B, surface life would not get to ignore the sky like that. If the planet has surface life at all, that life may be living under conditions where the star is always part of the survival problem, not sometimes, continuously. And this is where the balance gets important, because the case is still not closed. A Nature Astronomy paper discussing the system put the habitability problem in very direct terms. A visible superflare strong enough to kill known organisms has been observed from Proxima, and coronal mass ejections have also been detected. That is serious enough on its own. But even in that context, scientists still point out that M-dwarfs, stars like Proxima, may still host life-bearing planets. So the point is not that the idea of life there has collapsed. The point is that any life there would exist in a much harsher and less stable environment than people usually picture when they hear the words habitable zone. That is why Proxima B stays so compelling. If the answer were obviously no, the story would already be over. If the answer were obviously yes, the tension would also be gone. Instead, what makes this system so intense is that both sides of the argument stay alive at once. The star looks dangerous enough to strip atmospheres and damage surfaces. At the same time, scientists are not willing to rule out life around red dwarfs as a class. So Proxima B stays in this narrow, uncomfortable middle where habitability is still possible, but only under conditions that may be far more extreme than Earth taught us to expect. That's also why the star changes the meaning of energy itself. On Earth, people usually think of a star as the steady source that makes life possible. Sunlight drives climate, powers photosynthesis, and keeps the planet warm enough for liquid water. That basic picture is still true in the broader sense. Life needs energy, but Proxima forces a harder version of the same idea. Energy is not automatically helpful. Too much in the wrong form, delivered too violently, can destroy the exact chemistry life depends on. It can break molecules apart, it can heat and expand the upper atmosphere. It can help strip gases away into space. It can turn the star from a provider into a constant threat. And around Proxima, that line may not stay fixed. It may shift with time. One era in the star's history may be worse than another. One flare may do little, while repeated flares over long timescales may do major damage. A planet may survive one condition, but not 10 million years of it. That is why this system feels so unstable in the scientific sense. The question is not just how much energy the planet gets on average. The question is how that energy is delivered, how often, in what way, wavelengths, and for how long. Around a star like Proxima, the average number can hide a much harsher reality. So the threat here is not just that the star is active, it is that the star is active while the planet is forced to orbit very close. That combination is the real issue. If Proxima B were much farther out, the radiation problem would look different. If the star were calmer, the close orbit would look less severe. But the planet gets both at once, a tight orbit and an active red dwarf. That combination is exactly what makes the system feel dangerous even before you get into the harder atmospheric and magnetic questions later. And once you accept that, the whole tone of the story changes again. Proxima B is not a rocky planet sitting peacefully in the right temperature range. It is a rocky planet trying to exist near a star that keeps raising the difficulty. Every discussion about water, air, climate, or biology has to pass through that fact first. The star is not a passive source of light, it is the system's main hazard. That is why Proxima B feels more unsettling the more precisely you describe it. The numbers do not calm the story down, they sharpen it. A dim star, yes, but a magnetically loud one, a nearby habitable zone, yes, but one created by forcing the planet into a compressed orbit. Possible warmth, yes, but delivered inside a radiation environment that may be far harder on atmospheres and surface chemistry than anything Earth deals with. And that leads directly to the next problem, because once the star is this active, the phrase habitable zone starts sounding less reassuring. A planet can sit in the right zone for liquid water on paper and still be trapped in conditions that make real habitability much harder than the label suggests. The habitable zone sounds safe, but that label can hide the real danger. This is one of the biggest misunderstandings in exoplanet science. People hear habitable zone and think that means a planet is probably comfortable, probably wet, maybe even probably alive. That is not what the term means. It does not mean life zone. It does not mean ocean zone. It does not mean Earth-like. It only means the planet orbits at a distance where liquid water could exist on the surface if other conditions are right. And that if is doing almost all the work. A planet can be in the habitable zone and still have no water. It can be in the habitable zone and have no meaningful atmosphere. It can be in the habitable zone and still be too damaged by radiation, too chemically altered, or too exposed to keep liquid water on the surface for long. So the phrase sounds much more hopeful than it really is. It sounds like a promise, but it is really just a starting condition. That is especially important with Proxima B, because a lot of the public excitement came from that one label. Once you slow down and define it properly, the planet becomes much less simple and much more interesting. And Proxima B only sits in that zone because it stays extremely close to its star. That is the trade built into the whole system. Proxima Centauri is faint, so the planet has to orbit tightly to receive enough average energy for surface temperatures that might allow liquid water. That is why its year lasts only 11.2 Earth days. The orbit that makes the planet sound promising is also the orbit that makes it dangerous. The same closeness that gives it the right average heating may also expose it to stronger tides, stronger radiation effects, and much more serious atmospheric stress than Earth deals with. That is the key point. The habitable zone around a red dwarf is not a protected region. It is not a safe ring where all the problems suddenly disappear. It is a compromise. You move inward to get enough warmth, but by moving inward, you also increase the pressure from everything else the star can do to you. So when people say Proxima B is in the habitable zone, the correct response is not good, then it may be fine. The correct response is, good, now we need to ask what the price of that location is. And that price may have started long before the planet reached whatever condition it has today. This is where timing matters as much as distance. Even optimistic climate work on Proxima B says the planet may have gone through a runaway greenhouse phase early in its history, when the star was brighter in key high-energy wavelengths during its youth. That means the planet could sit in a potentially favourable orbit now, and still be carrying the damage from a much worse past. It could have lost large amounts of water early. It could have had its atmosphere heavily altered. It could have been pushed into destructive conditions millions or billions of years before any modern telescope ever looked at it. That makes the story much harder and much more serious. A planet is not judged only by where it is now. It is judged by what happened to it over time. Habitability is not just about current location, it is about history. If the star spent a long early phase blasting the planet with intense radiation, then being in the habitable zone today may not save it from the consequences of that earlier period. A world can end up in the right place and still arrive there already damaged. That is a big shift in how you think about these planets. It means you cannot just draw a neat ring around a star and count every rocky world inside it as a promising home for life. You have to ask what the star was like early on. You have to ask how much water the planet started with. You have to ask how quickly the atmosphere escaped, how long the surface stayed hostile, and whether anything stable was left after the worst phase ended. In other words, the habitable zone is not the answer. It is just one part of the question. And with Proxima B, the orbit makes that danger easy to understand because the numbers are so extreme. The planet is about 7.3 million kilometers from its star, around 4.5 million miles. Its year is 11.2 days. That means it is spending all of its time deep inside the star's magnetic and radiation environment. Earth orbits the Sun at about 150 million kilometers, around 93 million miles. That distance gives Earth room. It gives Earth a much wider buffer from the Sun's most direct influence. Proxima B does not have that kind of buffer at all. It lives close in all the time under conditions where the star is not just above it, but all around its long-term survival story. And that is why the difference is not small. It is not just that one planet is somewhat closer than the other. It is a different kind of planetary life. Earth gets warmth from a relatively stable star at a large orbital distance. Proxima B gets its possibly habitable temperature by staying close to a star that is smaller, more active, and harder on nearby planets. So even if both planets can be described with the phrase habitable zone, the reality behind that phrase is completely different. The same term covers two very different environments. That is what makes this section so important, because it forces you to separate the label from the physics. The label says possible liquid water. The physics says maybe, but only if the atmosphere survives, only if the water survives, only if the star does not remove both, and only if the planet can handle living this close for very long stretches of time. The label sounds easy. The reality is conditional at every step, and once you see that, a bigger problem appears. Red dwarfs are the most common stars in the galaxy. That makes them natural targets in the search for habitable planets. They are small, common, and easier in some ways for astronomers to study. So at first that sounds encouraging. If red dwarfs are everywhere, then maybe potentially habitable worlds are everywhere too. But Proxima B shows the darker side of that idea. The same stars that are common enough to offer many chances may also create some of the hardest environments for real long-term habitability. That is the cruel part of the math. One of the galaxy's most common routes to a potentially habitable planet may also be one of the most efficient ways to filter such planets out. You get lots of rocky worlds in the right temperature range on paper, but many of them may have to survive intense tidal effects, close-in radiation exposure, and early atmospheric damage just to stay in the game. So the abundance of red dwarfs does not automatically mean abundance of easy homes for life. It may mean abundance of difficult tests. And that is why Proxima B matters so much beyond this one system. It may be showing us something uncomfortable about the galaxy as a whole. The most common stars may produce many planets that look promising in catalogues, but that promise may come with built-in penalties. The zone that sounds like the beginning of hope may also be where the filtering starts. The most common homes may be the hardest homes to survive, and the next problem follows directly from that, because once a planet orbits this close to its star, distance is no longer the only thing shaping its fate. Rotation starts to matter in a much bigger way. And on Proxima B, the way the planet turns may decide whether parts of it stay survivable at all. The year lasts 11 days, and that already tells you this planet does not work like Earth. But the stranger part is not just how fast Proxima B goes around its star, it is how that tight orbit may control the way the planet turns. And once that happens, rotation stops being a background detail and starts deciding what kind of world this is. Because Proxima B orbits so close to its star, scientists generally treat it as likely to be tidally locked, or at least strongly affected by tides. That means the star's gravity may have slowed and shaped the planet's rotation over time. In the simplest version, one side of the planet always faces the star, while the other side stays in permanent darkness. The same face gets daylight at all the time, the other face never gets sunrise at all. Unless the planet is trapped in a different spin pattern, that is the basic setup you're dealing with. And this is not a small climate detail. This is not some extra fact added for atmosphere. It changes almost everything. It changes where the heat goes, it changes how winds move, it changes where clouds form and how stable they are. It changes whether the atmosphere can spread warmth well enough to stop one side from overheating and the other from freezing hard. It changes whether the planet becomes something stable and strange, or something split into regions that are too hostile for surface life almost everywhere. On Earth, when people talk about climate, they usually assume a world that rotates in a familiar way. Day and night move across the surface. Winds shift with rotation, seasons change over time. Oceans and air move heat around a globe that is constantly changing its orientation to the sun. That is the normal picture in your head. Proxima B may break that picture completely. If it is synchronously locked, the point directly under the star gets constant daylight. Not a long day, constant day, permanent noon. Meanwhile, the far side gets permanent night, not a long winter night, permanent darkness. That means surface conditions stop being one general idea and turn into a map problem. You may have one region that is always getting cooked by starlight, another region that is always losing heat into darkness, and between them, maybe a narrow band where temperatures are moderate enough for something interesting to happen. So the question stops being, is the planet habitable, and becomes much more specific. Which part of it might be habitable? A planet like this may not offer a global answer. It may offer a strip, a patch, a margin. That is a very different way to think about life. On Earth, Life spreads across a rotating world with many climates and many transitions between them. On Proxima B, if the locked world picture is right, life would be forced into geography much more aggressively. The day side might lose water more easily. The night side might become a trap for ice and frozen gases. The edge between them, the Terminator region, could become the most important place on the planet because it is the zone where the extremes begin to soften. The whole question of habitability may collapse into whether that compromise region is stable enough and wide enough to matter. But even that is not the only possibility. The story gets stranger because Proxima B may not be perfectly synchronized. There is another option scientists have discussed for a long time. The planet could be in a spin-orbit resonance, something like Mercury in our own solar system. In a 3-to-2 resonance, the planet rotates 3 times for every 2 orbits around the star. That sounds technical, but the result is simple. The same locations would not always face the star in exactly the same way, and the pattern of heating across the surface would be very different from a fully locked world. That matters a lot. A 3-to-2 state changes the thermal map of the planet. It changes where the hottest regions are and how stable they stay. It changes cloud patterns. It changes where liquid water might remain at the surface. It changes how the atmosphere circulates. It even changes what astronomers on Earth might detect later, because the light coming from the planet would vary differently over time. So the length of the day on Proxima B is not trivia. It is tied directly to climate, water stability, and even how future telescopes may interpret the planet. That is what makes this section so important. People hear orbit and rotation and think they're just technical parameters. On a planet like this, they are survival controls. If the planet rotates one way, you may get a stable climate pattern with some region that can hold liquid water. If it rotates another way, the same world may become much harsher. So one of the biggest questions about Proxima B is not just where it is how it moves. And this is where the world starts feeling truly alien in a practical sense, not in a flashy science fiction sense. If life exists there, its most basic experience of the environment may be completely different from ours. No normal sunrise crossing the horizon. No familiar cycle of day and night. No planet-wide pattern where photosynthetic life can spread under a moving sky in the way it does on Earth. Instead, you could get permanent environmental specialization. One side always losing water. One side always trapping ice and cold. One middle region carrying most of the planet's realistic chance for surface habitability. That pushes the whole idea of Earth-like even further away. You're no longer asking whether Earth life could move there easily. You're asking whether life that evolved there would think Earth is the strange planet. On Earth, the surface is constantly changing in light and temperature over time. On Proxima B, those changes might be dominated more by place than by time. Location could matter more than daily rhythm. A creature there might not organise life around sunrise and sunset at all. It might organise life around permanent zones. And once you get to that point, the tension increases again because rotation is no longer just shaping the weather. It may be deciding whether the atmosphere stays stable enough to prevent collapse. It may be deciding where liquid water can persist. It may be deciding what kind of spectral signals the planet sends into space when astronomers try to study it. Even our attempts to detect life from far away may depend on how this world keeps time, because different rotation states create different patterns in clouds, heat, and reflected light. So this is one of the most important shifts in the whole Proxima B story. On Earth, rotation matters a lot, but mostly in ways people experience as weather, climate patterns, and the length of the day. On Proxima B, rotation may be much closer to destiny. The planet does not just orbit oddly. It may live or die by the way its orbit and rotation lock together over time, and that leads straight into the next problem. Because once you accept that the world may be split into permanent climate zones, the simple version sounds easy. One side burning, one side frozen. But the real climate picture may be much stranger than that, and in some ways even more unsettling. One side burning and one side frozen sounds like a clean answer, but Proxima B does not stay that simple for long. The climate story gets stranger the more seriously scientists model it. And that is important, because the main result from the better climate work is not this planet is clearly dead. The real result is that Proxima B keeps refusing easy conclusions. Early on, it was tempting to picture a tidally locked world in the simplest possible way. Bright side too hot, dark side too cold, end of story. But once researchers started using better climate models, especially models that include moving oceans instead of treating the ocean like a still surface, the picture changed. NASA-hosted dynamic ocean simulations showed that an ocean-covered Proxima B could keep a much wider area of liquid water on the surface than older, static ocean models suggested. The temperatures in some of those cases were still cold by Earth standards, but the important point is that the planet may not break cleanly into habitable and uninhabitable halves. It may develop a more complicated set of climate regions than people first expected. That changes the tone immediately. Every time the easy disaster version starts sounding final, the climate physics opens another possibility. Not a comfortable one, but a real one. The planet may not be a dead rock with one hot face and one frozen face. It may be a world where circulation matters so much that water, air and ice keep pushing against the worst case outcome. That does not make the planet safe. It makes it harder to dismiss, and the oceans are a big part of that. On a tidally influenced planet, the ocean is not just scenery. It can move heat. If warm water from the day side can flow toward the night side, then the dark hemisphere does not have to become a complete deep freeze. If cold water can cycle back, then the hot side does not simply become one giant evaporation zone. The fight changes. Instead of the climate collapsing into two static extremes, the ocean can act like a transport system that redistributes some of the energy across the planet. That is why the 2019 climate work matters so much. It suggested scenarios where Proxima B could have a mostly open ocean and conditions that might even allow halophilic life adapted to salty environments. That is a very different picture from the simple headline version. The unsettling possibility may not be that the planet is just dead. It may be that it stays alive only in environments that are much colder, saltier and stranger than the public expects when they hear Earth-like. That is a big shift. Once you accept it, the real question is no longer surface ocean or nothing. Liquid water on Proxima B may not be global at all. It could exist in specific patches, in broad belts, or under ice. A moderate climate case might keep liquid water in a dayside region or in a band where heat transport and atmospheric circulation balance out. A colder or more water-rich case might leave the surface largely ice-covered, while still preserving liquid water below that ice. So habitability stops looking like a global blue planet and starts looking like a map full of limited refuges. And that is where the story gets more serious, because once buried liquid water becomes plausible, the whole search for life gets harder. A 2022 study modelled melting at the base of the thick ice on Proxima B and showed that under one case, with a 2-kilometre thick ice sheet and a surface temperature of 257 Kelvin, liquid water could form underneath within a few 100,000 years. That means the planet could end up with a protected liquid environment below a hostile surface. The surface can lose, and the deeper water can still stay in play. That one result changes the shape of the whole discussion. You are no longer dealing with a simple yes or no question about surface habitability. You are dealing with multiple layers of possible survival. Surface oceans are one option, partial open water zones are another, subsurface water under ice is another. So the more carefully you look, the less Proxima B resembles an Earth copy, and the more it starts looking like a world where life, if it exists, may survive in restricted and hidden places. And then chemistry makes the story even stranger. Salinity matters here in a way that people often underestimate. In the dynamic ocean studies, salt is not a small tweak. A highly saline ocean freezes at a lower temperature. That means the salt content can change how much water stays open, where ice forms, how deep circulation goes, and how stable the climate becomes in different regions. So now it is not just the star, the orbit, and the rotation shaping the planet. The chemistry of the water itself starts deciding the geography of survival. That is a powerful detail because it makes the climate feel less like one single temperature problem and more like a system of interacting pressures. How warm is the world? How much salt is in the water? How fast does the ocean move heat? How thick is the ice? Is the water trying to stay exposed, or is it slowly getting locked away? Those are not cosmetic details. They change whether the planet keeps accessible liquid water on the surface in narrow bands or only far below an ice cover. So the climate of Proxima B may be weird in a very specific way. Not random, not mysterious for the sake of it. Weird because every part of the system pushes against every other part. Tidal effects shape circulation. Circulation shapes ice. Ice and salinity shape where water stays liquid. And all of that happens under a star that may keep making the atmosphere and surface harder to preserve. It is not one problem. It is a stack of interacting problems that sometimes partially cancel each other and sometimes make each other worse. That is why the farther you go into the climate work, the less the question sounds like, is this another Earth? And the more it sounds like, what form of survivable can planetary physics produce under heavy stress? Maybe Proxima B is a cold ocean world with one permanent open region. Maybe it is mostly ice at the surface with liquid underneath. Maybe it is a planet that only stays habitable in a narrow zone, where heat transport barely keeps ahead of freezing and atmospheric damage. None of those outcomes are simple, none of them are comfortable, but they are scientifically serious. And in a way, that is more unsettling than finding a clear Earth twin. A second Earth would fit into a familiar category. Proxima B may not. It may be a world where life survives only in the margins, in high salt water under ice, or in regions where the climate never fully settles into either safety or ruin. That kind of habitability is harder to picture, harder to detect, and maybe much more common than the easy version we usually imagine. And that leads directly to the next problem, because all of these climate possibilities depend on one thing the planet may not be able to keep for long enough. The atmosphere may be the whole game, and there is a real chance it does not survive. The atmosphere may be the whole game, because if Proxima B cannot keep its air, almost every other hopeful detail stops mattering. A planet can sit in the habitable zone on paper, it can have the right mass, it can even start with water, but if the atmosphere gets stripped away, the surface story collapses very fast. That is why this part of the science matters so much. The question is not only whether the planet is warm enough, the question is whether the air can stay attached to the world long enough for liquid water and biology to mean anything at all. This is where the danger becomes much more technical, but also much clearer. The main issue is not just surface heat. It is what happens high above the surface where the star keeps dumping energy into the upper atmosphere. That energy can ionize gases, heat them, expand the upper layers, and make it easier for particles to escape into space. So when scientists talk about atmospheric loss on Proxima B, they are not describing ordinary weather. They are describing a long-term process where the planet may slowly lose the basic material needed for a stable surface environment. And for Proxima B, that threat is not small. NASA has pointed out that at this orbit, an Earth-like atmosphere may simply not survive. That one idea changes the whole meaning of the habitable zone. Because if the atmosphere goes away, then surface liquid water becomes much harder or impossible to maintain. Pressure drops, temperature control gets worse, radiation shielding gets weaker. Heat transport across the planet becomes less effective. So the phrase habitable zone starts meaning very little if the planet cannot hold on to the gases that make a surface environment stable in the first place. Then the radiation environment makes the problem even worse. Proxima B is thought to receive bursts of extreme ultraviolet radiation hundreds of times stronger than what Earth gets from the Sun. That is not a small increase. That is a completely different level of stress. Extreme ultraviolet light has enough energy to break apart molecules and drive atmospheric escape much more efficiently. At first, people may think of hydrogen as the main thing that escapes, because it is light and easy to lose. But over time, the damage can go beyond that. Heavier gases like oxygen and nitrogen can also be affected under strong enough conditions. That is the point where the stakes jump. You are no longer talking about a planet losing a little atmosphere here and there over long timescales in a manageable way. You're talking about the chemical framework of an Earth-like world being attacked piece by piece. The gases that support pressure, climate stability, and surface chemistry may be removed molecule by molecule. And if enough of that happens for long enough, then the planet may stop behaving like a surface habitable world even if it once had the ingredients. The contrast with Earth is brutal. Earth loses some atmosphere too, but slowly enough that it stays a living planet over billions of years. On Proxima B, some models suggest atmospheric escape could happen up to 10,000 times faster than the equivalent loss at Earth. That number is extreme enough to reset the whole discussion. Earth survives because the loss is slow and the system is stable enough. Proxima B may need unusual advantages just to avoid falling behind. It may need strong shielding, unusual atmospheric replenishment, or initial conditions much more favourable than Earth's just to stay in the game. And the danger is not limited to one past era. The problem may still be active now. X-rays, extreme ultraviolet radiation and stellar wind from Proxima Centauri can keep pressuring the atmosphere over long periods. So the planet may not only have suffered damage early in its history, it may still be under attack. That matters because a world can survive one bad chapter if it recovers. It is much harder to recover if the damage is persistent. This is also where the water story becomes much darker, because water loss can create one of the most misleading signatures in exoplanet science. A lot of people hear oxygen and immediately think life. On Earth that instinct makes sense because oxygen is deeply connected to biology, but around active red dwarfs that logic can fail badly. If ultraviolet radiation breaks apart water molecules, the hydrogen escapes more easily into space, and the oxygen can be left behind. So a planet can lose water and still end up with oxygen building up in the atmosphere. That means oxygen does not always mean a living world. It can mean the opposite. It can mean a world that lost oceans and kept part of the chemical wreckage. That is what makes Proxima B especially unsettling. Atmospheric escape does not only threaten habitability, it can also fake it. The planet might end up showing the chemistry people want to see while actually telling the story of a destroyed surface environment. That is a very dangerous kind of false hope. Because if future telescopes detect oxygen or oxygen-related signals around a world like this, that does not automatically mean forests, algae, or a thriving biosphere. It could mean ultraviolet light broke apart large amounts of water, hydrogen escaped, and oxygen remained as an abiotic leftover. In other words, the atmosphere may keep the appearance of a biosignature after the loss of the thing life needed most. So the atmosphere becomes more than a physical requirement. It becomes part of the interpretation problem too. If Proxima B kept a stable atmosphere, then life becomes much more plausible. If it lost that atmosphere, the surface may be dry, exposed, and badly damaged. And if it lost water while leaving behind oxygen, then the planet could even look more promising than it really is. That is one of the most disturbing possibilities in the whole Proxima B story. Not just that life may be absent, but that the evidence from far away could point in the wrong direction. That is why this section matters so much. The atmosphere is not one variable among many. It may be the variable that decides how all the others matter. Keep the air and climate, liquid water, and biology stay possible. Lose the air, and the whole surface picture can fall apart. Lose the water in the wrong way, and the planet may even advertise a false version of habitability to distant observers. So the darkest version of Proxima B is not simply a dead world. It is a world that may preserve the spectral leftovers of destruction. A planet that lost the conditions for surface life, but still shines with chemical signs that could fool us into thinking the opposite. That would make the nearest potentially habitable world even more troubling, because it would not just be hard to survive on, it would be hard to read correctly. And the next twist makes the uncertainty even worse, because there may be one thing that can protect the planet from some of this damage. A magnetic field could save a lot, and the problem is that we do not know whether Proxima B has one. The atmosphere story is not one-sided doom. And that actually makes Proxima B more unsettling, because now the answer may depend on something we cannot see directly. A 2024 magnetohydrodynamic study showed that if Proxima B has a magnetic field roughly comparable to Earth's average field, about 0.32 Gauss, then under calmer stellar wind conditions the planet could push that wind back far enough to give the surface meaningful protection in almost every tilt setup except the most extreme ones. That is a major change in the argument. The planet may not just sit there and take the full hit. If it can defend itself, then some of the worst atmospheric loss scenarios may be too pessimistic. That is a big turning point, because up to this point the story can sound like everything depends on how badly the star attacks the planet. But a magnetic field changes that. It gives the planet a way to resist. It does not stop the star from being violent, but it can reduce how much of that violence reaches the atmosphere and surface directly. So instead of one simple story where the star strips everything away, you suddenly get a split path. One version of Proxima B is exposed and vulnerable, another version is shielded enough to keep fighting. And the same study makes the case even stronger under harsher conditions. Even during more extreme coronal mass ejection-like space weather, an Earth-like magnetosphere could still provide substantial protection if the field strength and tilt are favourable. That is an important shift in tone. It means storms do not automatically end the case for habitability. The planet does not need a perfectly calm star to survive every time. It may just need the right internal machinery to absorb more punishment than the bleakest models assume. That is what makes the science here so tense. On one side, there are models saying the atmosphere could be stripped catastrophically under Proxima's radiation and stellar wind. On the other side, there are models saying a magnetized Proxima B might survive much more of that damage than people first thought. That is not confusion. It is not researchers cancelling each other out. It is a sign that one hidden planetary property may control a huge part of the outcome. And that hidden property is exactly what we do not know. We do not have a direct detection of a magnetic field on Proxima B. The planet does not transit in a way that gives us the easiest atmospheric methods, and we do not have a clean observational shortcut to the answer. So scientists are forced to model branches of possibility instead of measuring the truth directly. That is why Proxima B feels so frustrating and so important at the same time. The gap between a sterilized rock and a shielded ocean world may come down to an invisible engine inside the planet, and right now we cannot just look up and confirm whether that engine is running. That makes the uncertainty worse in a very specific way. If the problem were only the star, the story would already be simpler. But now the question runs inside the planet. Does it have a molten, active interior capable of driving a dynamo? Does it have the right core conditions to generate a strong magnetic field over long timescales? Does its rotation help or weaken that process? Does its tilt change how well that field actually protects the atmosphere under different space weather conditions? These are deep interior questions, and they may decide what happens to the surface. And even if the field exists, it is not a magic shield. This is important. A magnetic field does not suddenly turn Proxima B into Earth. In the more optimistic simulations, the protection is still conditional. Calm stellar wind is easier to handle than extreme space weather. Field strength matters. Tilt matters. The surrounding plasma environment matters. The geometry matters. A magnetic field can reduce particle precipitation and improve the odds of atmospheric survival, but it does not erase the red dwarf problem. It just changes the odds. That is exactly why this part of the story works so well. Every time you think you found the solution comes with another layer of conditions. If the planet has no field, the atmosphere may be in deep trouble. If it has a field, then you have to ask how strong it is. If it is strong, then you have to ask how it is oriented. If the orientation is good, then you still have to ask how often Proxima throws extreme space weather at it and how long that lasts. So the magnetic field does not close the case. It moves the planet from probably impossible to still in contention. That is a much more interesting and more unnerving place to be. Because now, habitability is no longer just about orbital distance and incoming energy. It is about planetary interior physics. It is about whether the core is active enough, whether heat is moving through the interior in the right way, whether the planet still has the conditions to sustain a magnetic dynamo, and whether that dynamo can shape a protective magnetosphere large enough to matter. The fate of the atmosphere may be decided not just by the star above, but by the metal and heat deep below. That is a big escalation in the Proxima B story. At first, the question looks simple. Is the planet in the habitable zone or not? Then it becomes harder. Can the atmosphere survive the star? Now it becomes harder again. Can the inside of the planet generate the shield needed to keep the outside survivable? The closer you get to the real science, the less habitability looks like a distance problem, and the more it looks like a systems problem, where orbit, atmosphere, star, and deep interior all lock together. And that makes Proxima B feel even more unstable as a mystery. The truth may depend on something thousands of kilometers below the surface, in a region we cannot observe directly. Iron, heat flow, rotation, and magnetic structure may decide whether the sky above the planet is merely harsh or completely destructive. The surface story may be written deep underground, and once you get to that point, another possibility opens up. Because if the surface is too exposed, too cold, or too difficult, water may still survive somewhere else. On Proxima B, the safest place for life may not be on the surface at all. It may be underground, under ice, hidden from almost everything that makes the planet so dangerous. Surface oceans are only one version of hope, and Proxima B may force us to think beyond that very quickly. One of the biggest Earth-based assumptions people make is that a habitable planet has to look something like our own world, with open water under an atmosphere and life working mostly at the surface. But Proxima B may not give us that kind of planet at all. Its climate history and water loss models leave room for a much colder and stranger outcome, where the surface is covered in ice, liquid water survives below, and whatever biology might exist is protected under a shell instead of living in the open. That possibility makes the planet more disturbing and more believable at the same time. More disturbing because it means life may not need the kind of easy surface environment people usually imagine. More believable because buried water is much better protected from flares, radiation, and charged particles than exposed oceans are. So once you stop insisting on a second Earth, Proxima B starts opening another path. It may be less like Earth and more like a much larger version of Europa, except around another star and on a planetary scale. That shift matters because water-rich composition is still a serious possibility. Internal structure studies have suggested that Proxima B could, in some scenarios, contain a very large amount of water, possibly up to around half its mass, although the real number is still unknown. That is a huge difference from Earth. A planet with that much water would not behave like a rocky world, with continents and ordinary oceans spread across the surface. It would store heat differently, freeze differently, circulate differently, and separate potentially habitable environments into layers instead of keeping them all at the top. That is why Proxima B becomes more scientifically interesting every time it stops looking familiar. A water-rich world does not just ask whether it is warm enough for a surface sea. It asks how deep the water is, how much of it freezes, what pressure builds up at lower levels, and whether liquid zones can persist below an ice shell for very long periods. So the more alien the composition gets, the less useful the Earth comparison becomes. And that is not a weakness in the story. It is the reason the story gets more serious. Ice is also not the end of the story. That point is critical. When people hear that a planet may be ice-covered, they often treat that as the end of the habitability discussion. But on Proxima B, ice may be part of the survival mechanism. In one modelled case, a study looked at a 2-kilometre thick ice sheet with a surface temperature of 257 Kelvin, and found that melting at the base could create a liquid ocean around 800 metres thick underneath. That means the planet does not need a warm, open surface ocean to keep water in play. The surface can freeze and liquid water can still exist below the damage. That gives Proxima B a very different kind of resilience. The water may survive by moving underground and letting the ice absorb the punishment from above. The surface can take the radiation, the temperature swings, and the harsh space environment, while the deeper liquid layers remain more stable. If that is how the planet works, then surface failure does not automatically mean biological failure. The surface can lose, and the hidden ocean can still keep the basic conditions for life going. And that possibility is unsettling for another reason. A buried ocean solves one problem by creating a new one. Yes, subsurface water is better shielded from the star. Yes, it gives life a safer place to survive, but it also makes life much harder to detect from Earth. A surface ocean can affect the atmosphere more directly. Surface biology can, at least in principle, leave stronger chemical signals. A buried biosphere under kilometers of ice may not do that in any obvious way. The planet could look cold, silent, and lifeless from the outside while still hiding liquid reservoirs and maybe even biology below. That is what makes hidden oceans so important to this story. They make Proxima B scientifically more plausible as a life-bearing world, but observationally more secretive. You could be looking at the nearest potentially habitable planet beyond the solar system and still learn almost nothing about what matters most if the real action is happening deep below the surface. The world may be close in distance and still extremely far in terms of certainty, and this is where the tension changes again. Up to this point, most of the fear has been environmental. Radiation, atmospheric stripping, tidal effects, surface climate. But now the problem becomes observational too. The more life retreats into protected niches, the less visible it becomes to our telescopes. The more successful the survival strategy is, the worse it is for detection. That is a brutal twist. The safest life may be the hardest life to prove exists. So Proxima B may be dangerous in two different ways at once. It may be physically hostile on the surface, and it may also hide the evidence if life survives below that surface. That means even better telescopes may still face a deeply frustrating target. A planet can keep water by burying it. A biosphere can survive by becoming hidden. And the same hidden structure that protects life can make the world look quiet from far away. That is why this idea lands so hard. The planet may be closest to us precisely where it is hardest to truly know, not because the science is weak, but because the most survivable version of the planet may also be the most difficult one to read. A buried ocean world around the nearest star would not just challenge biology, it would challenge our whole method of searching for life with remote observations. And that leads to the next problem, because even if life survives there, it may not work the way life works here. The light from Proxima Centauri is very different from sunlight, and that means any biology on Proxima B may have to run on a version of life that is much less Earth-like than most people expect. If life exists on Proxima B, it may run under a kind of light that Earth life would find difficult from the start. That matters because the star does not illuminate the planet the way the sun illuminates Earth. Red dwarfs like Proxima Centauri produce much less of the visible light range that Earth plants and algae use most effectively for photosynthesis. So even before you get to flares, radiation, or atmospheric loss, the basic energy budget for surface biology may already be different. That creates a major shift in how you think about life on the planet. On Earth, biology is often limited more by nutrients, water access, temperature, or local chemistry than by the total number of usable photons. There is usually enough sunlight for photosynthesis somewhere in the system. On Proxima B, that may not be true in the same way. If life depends on Earth-like oxygen-producing photosynthesis, then the problem may begin with not having enough useful visible photons in the first place. Life may not first be competing for minerals or space, it may first be competing for workable light. That sounds bad for habitability, but this is another case where Proxima B refuses the simple answer. More recent studies and lab simulations make the picture less straightforward. A 2023 experiment found that cyanobacteria exposed to simulated M-dwarf starlight were still able to support biological oxygen production at levels similar to solar-like conditions at the tested intensity. That does not prove surface photosynthetic life exists on Proxima B, but it does weaken the old easy argument that red dwarf light automatically shuts the whole story down, and the reason is simple. Biology may adapt. Theoretical work suggests that organisms could evolve more efficient light harvesting systems, or shift toward using longer wavelengths more effectively than Earth plants do now. So the question may not be whether Earth's exact kind of photosynthesis works unchanged. The question may be whether life can solve the light problem in a different way. Around a star like Proxima, evolution may not need familiar sunlight. It may only need a way to capture enough energy from a dimmer, redder environment. That is where the biology starts getting stranger. If usable visible light is limited, then any surface biosphere on Proxima B may have to be very efficient, very localized, or very different from the ecosystems people usually picture. It may rely on pigments that work farther into the red or near-infrared. It may exist mostly in regions where conditions make light collection easier. It may live slowly compared with Earth ecosystems. It may not produce huge planet-wide oxygen output, even if it is biologically active. So once again, the problem is not simply too little light. The problem is that the light may select for unfamiliar solutions. Then the flare question makes the biology even more unsettling. Flares are destructive, but they may also create short periods where the light environment changes in a useful way for certain organisms. During a flare, the star can produce more short-wavelength radiation than usual. That is dangerous, can damage DNA, stress cells, and worsen atmospheric problems. But if some organisms are adapted to survive the downside, those same events may briefly increase the availability of photons that are useful for photosynthetic or related chemistry. That means the same stellar behavior that threatens life may also create temporary opportunities for it. That does not make flares harmless. It makes the biology harder to imagine in Earth terms. On Earth, a stable energy supply is usually treated as an advantage. On Proxima B, some life might evolve around instability itself. It might endure long periods of low energy conditions and then exploit bursts of higher energy light when they arrive. In other words, if life is there, it may not just survive danger, it may be built to use danger as part of its energy environment. That is a disturbing possibility because it pushes life away from the Earth model again. Instead of a globally bright world supporting widespread photosynthesis, you may get a biosphere that is patchy, low-light adapted, flare-aware, and tuned to a star that behaves in pulses rather than in a smooth, familiar way. The planet may not host forests, broad oxygen-rich ecosystems, or anything that leaves a strong Earth-style signal. It may host microbial specialists, thin biological films, subsurface communities, or surface organisms that live under a very narrow set of conditions, and that brings up another problem. Oxygen may not even be the main biological signature on a world like this. If visible light productivity is limited, then Proxima B may never develop the kind of oxygen-heavy atmospheric history that makes Earth so easy to interpret in hindsight. Its biology, if it exists, may stay small, local, or metabolically different. It may be dominated by low-light specialists, it may live under ice, inside saline water, or in microbial ecosystems that do not pump large amounts of oxygen into the atmosphere. So even if the planet is alive, it may not advertise that fact in the way we most want it to. That is one of the most unsettling parts of the whole Proxima B story. Life may be there and still remain spectrally quiet. The fingerprints we learn to trust from Earth may not show up clearly. The atmosphere may not be strongly oxygenated by biology. The surface may not be covered in obvious photosynthetic pigments. The biosphere may stay hidden, sparse, or chemically subtle. So the challenge is not only whether life exists, the challenge is whether life there would produce signs we are even prepared to recognize. And that pushes the whole question into bigger territory. If biology can adapt to dim red light, to burst-like flare illumination, and to long-term environmental stress, then Earth stops looking like the standard model of life and starts looking more like one relatively easy example. Proxima B matters because it forces that possibility into view. Life may not need comfort, stability, or sunlight light as much as people assume. It may need only enough energy, enough protection, and enough time to become highly specialized. That is why this section changes the stakes. The terrifying possibility is not just that life could exist on Proxima B, it is that life could exist there in a form that makes Earth look unusually simple. A world with weaker visible light, violent flares, and a harsher climate may still support biology if that biology is efficient enough, flexible enough, and strange enough. That possibility makes the universe feel less familiar and much less easy to classify. And the next problem is even worse, because even when we do get the chemistry, one of our oldest signs of life may be able to lie to us. Around a planet like Proxima B, oxygen itself may not mean what we want it to mean. Oxygen could lie to you, and that changes the whole search for life. For a long time, oxygen was treated as the strongest biosignature because on modern Earth it is closely tied to biology. That logic made sense. If you saw a lot of oxygen in an atmosphere, the natural reaction was to think of photosynthesis, ecosystems, and a living planet. But that picture is no longer enough. Scientists now take a much more careful view, especially for planets around red dwarfs. Oxygen can be made without life under the wrong conditions, and Proxima B may be exactly the kind of world where that becomes a serious problem. That is where the story gets darker. Around M dwarfs, water loss and photochemistry can create oxygen or ozone in ways that look promising at first and completely misleading on closer inspection. So the question is no longer just could we detect oxygen? The harder question is, what kind of oxygen are we looking at? Is it being produced and maintained by biology, or is it the chemical leftover from a planet that lost its water and never recovered? That is a huge difference, and Proxima B sits right in the middle of that uncertainty. This is why the oxygen issue is so unsettling. If Proxima B went through heavy early water loss, ultraviolet radiation could have broken water molecules apart, allowed hydrogen to escape into space, and left oxygen behind. In that case, a strong oxygen signal would not mean forests, oceans full of photosynthetic microbes, or a healthy biosphere. It could mean the exact opposite. It could mean the planet once had water, lost it, and kept part of the chemical residue after the damage was done. So one of the strongest signs of life could also become a sign of planetary failure. That changes the emotional logic of the whole search. Oxygen stops being simple evidence of life and starts becoming something that needs to be investigated like a crime scene. The planet may wear the chemistry of life after losing the conditions that life needed most. That is one of the harshest lessons in modern exoplanet science. A world can carry a signal that looks alive, while actually recording the history of its own destruction. And Proxima B is almost built to trigger that fear. It is close to an active red dwarf. It may have suffered strong ultraviolet radiation early in its history. It may have been vulnerable to atmospheric escape and water loss for the long periods. Those are exactly the conditions where a biotic oxygen becomes a serious false positive pathway. So if future telescopes detect oxygen around Proxima B, that would be exciting, but it would not be enough. It might be a sign of life, or it might be the chemical monument left behind by a dead ocean. That is why scientists are already building methods to catch that lie. Recent work on nearby non-transiting planets, including Proxima B, puts a lot of emphasis on combinations of gases rather than single detections. The point is simple. Context matters more than one molecule. Oxygen by itself can mislead. But oxygen together with the right amount of methane, or carbon dioxide with methane in the right kind of disequilibrium, becomes much harder to explain without biology. Researchers are also looking at other spectral clues that can reveal whether an oxygen-rich atmosphere is too thick and too dry to be a healthy biosphere. That is where the science gets very sharp. Some studies note that strong oxygen-oxygen collision features can help identify atmospheres that are rich in oxygen because of past ocean loss rather than active biology. In plain language, the spectrum may contain the clue that exposes the fraud. The atmosphere can carry its own warning sign if you know what pattern to look for. So the goal is not simply to find oxygen. The goal is to figure out what story the oxygen belongs to. That is a much more mature standard for the search for life. Scientists are not just looking for one gas anymore. They are looking for a self-consistent planetary story. Does the atmosphere make sense if life is present? Does it also make sense if life is absent? Is the star's ultraviolet environment strong enough to create false positives? Is there evidence of water loss? Is methane surviving in a way that should not happen without constant replenishment? Does the chemistry fit a living world, or does it fit an irradiated leftover? Those are the kinds of questions that matter now, and Proxima B may be the place where this standard gets tested hardest. Because it is nearby, because it is difficult, and because it sits right at the boundary between hopeful and deceptive. It is exactly the kind of world that can force the field to grow up. A simple oxygen detection there would be a beginning, not an ending. It would start the hardest part of the argument, not settle it. That makes the whole thing more psychologically unsettling. A world can look alive and be dead. A world can be alive and look dead. That is the real nightmare hidden inside Proxima B. The nearest plausible life-bearing planet may end up proving that one spectral line is never enough. You may need to build the case the way a courtroom builds a case, piece by piece, from atmospheric chemistry, climate models, stellar activity, orbital behaviour, and planetary history. And that means the universe may not give us simple verdicts, not on the nearest target, not even when the data starts getting better. Proxima B may force us to leave behind the comforting idea that one beautiful detection settles the biggest question in science. Instead, we may get a world where every promising sign demands another layer of doubt and another layer of explanation. And the next reason that doubt stays so strong is deeply frustrating. We cannot just wait for the easiest kind of atmospheric measurement, because Proxima B does not give us that option. The planet keeps one of its biggest secrets by refusing to line up in the way astronomers would most like. We cannot just wait for a transit, and that is one of the biggest reasons Proxima B stays so frustrating. A large part of modern exoplanet atmosphere science depends on transits. That is when a planet passes in front of its star from our point of view, and a small amount of starlight filters through the planet's atmosphere. That filtered light can carry chemical information. It is one of the cleanest and most powerful methods astronomers have for studying alien atmospheres. But Proxima B probably does not transit. And that single fact blocks the easiest road to answers. That matters more than people usually realise. If Proxima B did transit, astronomers would have a much better shot at measuring its radius, getting stronger constraints on its atmosphere, and building a more complete physical picture of the planet. But because it probably does not cross the face of its star from our line of sight, we lose that shortcut. So the nearest potentially habitable planet around another star is also one of the most observationally difficult Sirius targets. That is why it stays famous and frustrating at the same time. It is nearby enough to matter enormously, but not cooperative enough to answer the easiest questions. And the missing transit creates another problem immediately. We do not know the planet's true mass cleanly. The method that found Proxima B is radial velocity, which measures how the star wobbles under the pull of an orbiting planet. That gives a minimum mass, not the exact one, unless you also know the angle of the orbit very well. So when people say Proxima B has a mass a little above Earth's, that number is a flaw, not a full reveal. The real mass could be higher. That is not a minor technical note. The actual mass affects composition, gravity, atmospheric retention, and surface conditions. A somewhat more massive planet may hold on to its atmosphere differently. It may have a different interior structure. It may have different tectonic or magnetic behaviour. So even one of the most basic facts about the nearest potentially habitable exoplanet is still partly hidden from us. We are debating the chances for life on a world whose weight is not fully pinned down. That missing information spreads outward into almost everything else. If you do not know the exact mass, it is harder to know the density. If you do not know the density, it is harder to infer the composition with confidence. If you do not know the composition, it becomes harder to judge the planet's surface gravity, interior structure, magnetic potential, and long-term atmospheric survival. So one missing geometric fact: the orbital inclination quietly makes a large fraction of the whole picture less certain. That is why Proxima B has become such a technical challenge for astronomy. Without transits, the usual easy path is closed, so scientists have to use much more demanding methods. They have to think in terms of high-contrast reflected light observations, high-resolution spectroscopy, interferometry, phase curves, and giant future telescopes with enough power to separate the tiny planetary signal from the overwhelming glare of the star. That is not just extra work. It changes the planet into a test case for the future of the field. So Proxima B is not only scientifically important because it may be habitable, it is important because it is forcing astronomy to become more capable. It is one of the closest and hardest serious targets for learning how to study an Earth-sized, non-transiting planet around another star. In that sense, the planet is not just waiting to be observed. It is pushing our methods to improve. It is a target that exposes the limits of the tools we already have. And this observational blindness matters a lot for the story itself, because once the easiest method is gone, uncertainty grows almost everywhere. Atmospheric composition becomes harder to measure. Cloud cover becomes harder to constrain. Albedo, how reflective the planet is, becomes harder to pin down. Magnetic shielding remains indirect. The true mass stays uncertain. Surface conditions stay model-dependent. So every confident headline about Proxima B is resting on a platform with major missing pieces underneath it. That is what makes the planet feel so difficult in a way that goes beyond the science headlines. The unsettling part is not only what Proxima B might be. The unsettling part is how close it is and how much it still refuses to tell us. It is close enough that people naturally expect clarity, but nature does not care about that expectation. The nearest promising world is still allowed to hide behind geometry, and that turns Proxima B into something larger than one exoplanet. If the nearest serious target is this hard, then the search for life is telling us something important about itself. Even when a world is practically next door by interstellar standards, the universe may still block the simplest path to certainty. We may not get clean answers from the most obvious techniques. We may have to invent new tools, new strategies, and new ways of combining weak signals into stronger conclusions. That is why Proxima B feels like a tutorial in scientific humility. It reminds us that closeness does not guarantee clarity. Being nearby does not mean being easy to understand, and in some ways that makes the planet even more important. It is not only a candidate for life, it is a training ground for how humanity will study the hardest and most valuable worlds in the future. And the tension gets even bigger once you remember that Proxima B is not alone. It sits inside a larger system, and that means habitability is not just about one planet and one star. It is also about neighbours, orbital interactions, and a whole local environment that may keep changing the rules. Proxima B is not alone, and that makes the whole story more complicated. It is easy to talk about this world as if it is one planet facing one dangerous star, but that is not the full system. In 2022, ESO announced Proxima D, an inner planet orbiting only about 4 million kilometers from the star, roughly 2.5 million miles, with a year of just 5 days. The same work also kept attention on Proxima B as the known 11.2-day habitable zone planet and mentioned a longer period outer planet candidate with an orbit near 5 years. So this is not just one rocky world in isolation. It is a compact system, and once you have multiple worlds, habitability stops being a one-planet question. That matters because nearby planets can change each other's long-term behaviour. Even if they do not crash into each other or cause obvious chaos, they can still affect orbital shape, timing, and tidal history. And for a planet like Proxima B, those details matter a lot. Small changes in eccentricity can change how much tidal heating the planet gets. They can affect whether the planet ends up fully tidally locked or caught in a different spin state like a 3-to-2 resonance. They can affect how much internal energy is generated, how the climate evolves, and how stable different surface or subsurface environments stay over time. So the neighbouring planets are not just extra names in the system. They may have helped shape Proxima B's rotational destiny, and that means they may also have helped shape its climate. If Proxima B's orbit was perturbed over long periods, then its tides, its interior heating, and its final spin state may all carry the signature of the larger system around it. This is important because it widens the danger. The planet may not just be dealing with the star, it may also be carrying the long-term effects of a crowded and dynamically active neighbourhood. That is especially clear when you look at Proxima D. This inner planet orbits even closer to the star than Proxima B does, in a region that is even more exposed to stellar violence. Its existence tells you something basic about this system. Proxima Centauri does not just happen to host one planet in an interesting orbit. It seems capable of building and keeping planets in very tight, intense configurations close to the star. Even if Proxima D is too hot and too exposed for surface life as we know it, it still changes how you think about Proxima B. It makes B look less like a lone lucky case and more like one member of a system that naturally forms compact, high-stress architectures. That is a more unsettling frame because now Proxima B starts to look like part of a pattern instead of an exception. The system seems comfortable placing planets deep inside the star's sphere of influence. That tells you something about planet formation there, but it also tells you something about the kind of environments those planets have to survive. Proxima B may be the most interesting member of the system for life, but it may also be one product of a system that regularly creates difficult orbital setups. And the better our instruments get, the less simple the system looks. That is another important point. Tools like Espresso have been crucial for confirming Proxima B and detecting Proxima D. The precision has become extraordinary down to tiny stellar motions measured at the level of tens of centimeters per second. That is a huge technical achievement. But higher precision does not always make the picture cleaner. Sometimes it does the opposite. It reveals more planets, more overlapping signals, more complications from stellar activity, and more ways the system refuses to be reduced to one neat story. That is actually perfect for understanding why Proxima B remains so difficult. Better data does not always make the target simpler. Sometimes it reveals that the target was sitting inside a more tangled system all along, and with a red dwarf star that is already magnetically active, separating planetary signals from stellar behaviour is hard enough by itself. Add more planets, more possible interactions, and more subtle orbital effects, and the whole picture becomes even harder to read cleanly. So by this point the question has changed. It is no longer just can Proxima B host life? That version is too narrow now. The more honest question is much bigger. Can a planet remain stably habitable inside an active red dwarf system with multiple worlds, uncertain spin history, strong tides, atmospheric risk, and incomplete observations? That is a darker question, but it is also the right one. Proxima B is not a simple laboratory example. It is a real planet in a real system, and real systems keep adding complications. That is why this world feels more intense the more complete the picture becomes. It is not being shaped by one factor. It is being shaped by the star, by its own interior, by its atmosphere if it has one, by its rotation, and probably by the long-term gravitational influence of its neighbours. Every layer you add makes the system feel less stable and less easy to classify. Proxima B may not just be trying to survive its star. It may be trying to survive the entire local architecture around that star, and that makes the stakes larger than one planet. Because if systems like this are common around red dwarfs, then the search for life is not just about finding a rocky world in the habitable zone. It is about asking whether that world can stay stable inside a whole environment that keeps pushing and reshaping it. Habitability becomes systemic. It depends on whether the larger neighbourhood allows long-term survival, or keeps nudging the planet into harder states. That is the more honest and more unsettling version of Proxima B. It is terrifying not because it is a single dramatic exception, but because it sits inside a real gravitational and magnetic neighbourhood that may keep shaking it over time. The planet is not standing alone under a red sun. It is part of a compact, active system that may keep rewriting its conditions. And that leads directly to the next turning point. Because for years, Proxima B lived mostly as a battlefield of models and arguments. But the next generation of telescopes may finally force the planet to answer with real observations instead of guesses. The next telescopes may finally force Proxima B to answer, and that is where the story stops feeling distant and starts feeling close. For years, this planet has lived mostly inside models, simulations, and arguments. Scientists could estimate, compare and debate, but the hard limits of current observations kept a lot of the biggest questions open. That may change in the next decade. And that is why this section matters so much. The mystery is no longer only theoretical. It is moving toward a phase where instruments may start cornering the planet with real evidence. Proxima B is one of the best targets for that kind of work because it is so close to Earth. It appears again and again in studies as the benchmark case for future direct characterization of a rocky, non-transiting planet. That is exactly why the extremely large telescope matters here. ESO's ELT is being built with a main mirror 39 meters across, about 128 feet. That is an enormous machine by any standard, and it exists for exactly this kind of problem. A planet like Proxima B is one of the clearest reasons to build something that powerful. It is nearby, small, difficult, and scientifically explosive if we can finally get real atmospheric and reflected light data from it. That is what makes the next phase exciting in a very concrete way. This is not just future telescopes will help somehow. The science goals are becoming specific. Recent simulation studies suggest that nearby non-transiting planets like Proxima B may be reachable for searches for molecules such as oxygen, carbon dioxide, methane, and water vapor with ELT plus observations under favourable assumptions. That does not mean the answer is guaranteed, it means the question is becoming operational. People are no longer just asking whether such measurements would be nice to have, they are estimating how many hours it may take, what combinations of gases may be detectable, and what kinds of atmospheres may be ruled out first. And some of those estimates are already sharp enough to feel real. One 2025 study argued that for a target as favourable as Proxima B, an ELT might be able to rule out a sub-Neptune type atmosphere in about an hour, and under optimistic assumptions could reach disequilibrium gas pairs like oxygen plus methane or carbon dioxide plus methane in around 10 hours. That is an extraordinary shift. Not because it guarantees biosignatures, but because it turns the search into something targetable. Proxima B is no longer just a planet people hope to understand one day. It is becoming a planet that future observatories may interrogate in structured campaigns. Oxygen is still one of the hardest goals, but it is no longer pure fantasy. A broader 2024 survey of Giant Magellan Telescope and ELT biosignature prospect suggested that a small set of known super-Earth candidates, including Proxima B, could be probed for Earth-like oxygen levels with about a week of observations on the ELT. That is a difficult measurement, but it is still within the language of practical observing, not science fiction. And another 2026 review discussing Proxima B in reflected visible light gave an even sharper sense of what may be coming. It described the planet-star brightness contrast as around 1 part in 10 million and estimated something like 50 hours of exposure for a strong reflected light detection that could help constrain the orbital inclination, true mass, and albedo. That one point is worth slowing down for because it shows how big the jump may be. Proxima B was discovered through the star's wobble. That means most of what we know still comes indirectly. But in the near future, the nearest potentially habitable exoplanet may move from being an inferred mass signal to being seen in reflected light. That is a major transition. It means the planet may stop being only a model input and start becoming an object that gives us its own measured photons. And even if those observations do not find what people hope for, the result is still huge. This is one of the most important parts of the whole story. Suppose the ELT looks and finds no useful atmosphere, no reflected light properties consistent with an Earth-like rocky world, or a spectrum pointing toward a dry and battered remnant. That would still be one of the most important outcomes in exoplanet science. Proxima B would become the nearest detailed case study in red dwarf habitability failure. It would tell us that even the best nearby candidate can lose the conditions people care most about. On the other hand, if the planet shows carbon dioxide, water vapor, methane, oxygen, or some combination that fits into a coherent planetary story, then the impact is just as large in the opposite direction. The search for life around red dwarfs would change immediately. The debate would not end, but the terms of the debate would shift. Suddenly, the nearest active red dwarf system would no longer just be a warning case, it would become strong evidence that planets in these systems can hold on to atmospheres and maybe more. That is why the next data do not merely refine the story, they rewrite it. Proxima B is not at the stage where a new observation would just adjust a detail or improve a parameter slightly. The new observations may decide whether this world is a dry cautionary example, a hidden water world, an atmosphere-bearing rocky planet, or something even stranger. The range of possible futures for the story is still wide, but the space for pure ambiguity may start shrinking, and that is what makes this moment genuinely tense. For a long time, Proxima B has been protected by uncertainty. The lack of direct evidence allowed many versions of the planet to stay alive at once. A stripped world, a shielded world, a cold ocean world, hidden ocean world, a false positive oxygen world, maybe even a biologically active world. Better telescopes threaten all of those possibilities at the same time, because they will begin forcing some of them out and narrowing what remains. So this is where the mystery enters the measurable phase. The argument is starting to move from mostly theoretical combat into observational combat. The planet that sat comfortably inside competing models may soon be pulled into evidence. And that is unsettling in its own way, because ambiguity has been part of what made Proxima B so powerful. Once the data arrive, some of the most dramatic possibilities will die, others may survive, and a few may become much harder to ignore. That is why the tension is not only about whether life is there, it is also about whether we are getting close to the point where we can no longer hide behind uncertainty. The truth may still be difficult, but it may no longer be too far away to test, and that is the scariest kind of development in this story. Not that the answer is safely distant, but that it may soon be close enough for us to start reaching. And once that happens, another thought becomes much more real. If this planet matters enough to drive telescope design and decades of observation, then it also matters enough to make people think about going there. And that is where the science runs into something even harsher. Proxima B is nearby in astronomy, but reaching it is still an engineering nightmare. Proxima B is near only by astronomical standards, and that is what makes it feel so strange. When you hear that it's a little over 4 light years away, it sounds close. It sounds like the neighbour star, the obvious next step, the place you would go first if you ever left the solar system. But that feeling disappears as soon as you turn the distance into travel. With ordinary spacecraft technology, the trip is not just difficult, it is effectively impossible on human timescales. That is why Proxima B sits in such an uncomfortable place in the mind. It is close enough to become a serious scientific target, and still far enough to stay almost untouchable. That is part of what gives the whole story so much tension. This is not some planet so far away that nobody can seriously think about it except in abstract terms. Proxima B is close enough to dominate future telescope plans, close enough to shape how people think about the search for life, close enough to become the first really serious destination in a lot of interstellar mission concepts. But it is also far enough that normal rockets are nowhere near enough. The same planet that feels like the next place to study also feels like a wall when you ask how to get there. And that is exactly why ideas like Breakthrough Starshot exist. Proxima B is one of the only exoplanets important enough to make people seriously discuss plans that sound extreme even by space science standards. The concept is simple in outline and brutal in execution. Tiny gram-scale spacecraft attached to light sails, pushed by giant Earth-based lasers to about 20% of the speed of light. At that speed, the trip to Proxima Centauri could take around 20 years. That number is so far beyond normal spacecraft thinking that the comparison almost stops making sense. 20% of light speed is about 60,000 kilometers per second, around 37,000 miles per second. That is not fast in the usual engineering sense. That is a completely different category. And the fact that people even talk this way tells you how important Proxima B is. Nobody proposes enormous laser arrays and wafer-thin interstellar probes for some random distant exoplanet. Proxima B gets that attention because it is the closest plausible rocky world in the habitable zone that we know. That moves it out of the category of background astronomy and into something much more serious. It is not just a discovery in a paper. It is one of the very few exoplanets humanity has looked at and thought, that is a place we might try to reach, at least with machines, within a meaningful future. That matters because it changes the emotional scale of the science. This is no longer just cosmology in the background. It is a possible destination. A brutal, difficult, almost absurd destination, but still a destination. That makes every discussion about its atmosphere, water, magnetosphere, or biosignatures feel more immediate. The closer the science gets to real characterization, the more the planet starts feeling like a place instead of a concept. But even the most ambitious mission idea makes it clear how far away we still are. A flyby at 0.2 C is not a careful visit. It is a violent pass through the system. At that speed, you do not slow down and take your time. You rush through. You deal with the interstellar dust hitting at extreme velocity. You deal with navigation over light years at relativistic speed. You deal with communications delays and weak signals coming from tiny probes. And you ask a very small payload to do nearly impossible science during a short encounter with one of the most important planets humanity has ever found. That is a hard truth to keep in view. Even if Proxima B really does host life, we are nowhere near a future where people casually go there and look for it directly. The nearest possible alien biosphere could become spectroscopically visible long before it becomes physically reachable in any practical way. We may learn a lot from photons while still being completely unable to touch the world those photons came from. That gap between knowledge and reach is what makes Proxima B feel so intense. You may live to see its atmosphere constrained. You may live to see its reflectivity measured. You may live to see strong arguments about water, carbon dioxide, methane, or oxygen based on real observations instead of only models. The coming decades may take this planet from a mostly theoretical object to a world with a much clearer profile. But almost nobody alive today is likely to see humans walk there. That is what gives the whole story a strange emotional pressure. It is close enough to know and too far to touch, and that is why Proxima B feels more real than most exoplanets. It is not only scientifically important, it occupies a specific place in human curiosity. It is near enough to haunt long-term planning, near enough to justify building giant telescopes, near enough to inspire interstellar probe concepts, and still distant enough that every one of those plans turns into a brutal engineering problem the moment you try to make it concrete. So when people say Proxima B is nearby, that is true only in the cold language of astronomy. In the human sense, it is still unbelievably far. It is the nearest possible answer to one of the biggest questions we have, and it remains almost impossibly distant in physical terms. That is part of what makes it so unsettling. The universe has put the most tempting target just close enough to matter, and still far enough to stay beyond our hands. And that sets up the final turn in the whole story, because by now the question is no longer just whether Proxima B is alive. The deeper question is what either answer would mean. If life survives there, it changes what we think life needs, and if it does not, that may be almost just as disturbing. If life survives on Proxima B, that does not give you a comforting ending, it gives you a harder universe. Because for life to exist there, it would have to survive conditions that already sound extreme before you even add biology into the picture. It would have to survive the close orbit, the tidal stress, the flare activity, the redshifted light, and the long threat of atmospheric loss. It would have to survive on a planet where the atmosphere may be fragile, where water may need to hide, and where the star keeps raising the difficulty. If life can make it there, then life is not just adaptable in the mild way people usually mean. It is much tougher than that. It becomes something that can keep going under pressure most people would have assumed was disqualifying. That changes the meaning of habitability immediately. Life would not just be a thing that appears on comfortable planets with sun-like light and long-term surface stability. It would be something that can endure a hostile star, weird climate geometry, and a much narrower path to survival. That is not a soft conclusion. It means Earth may not be the normal template people unconsciously use. It may just be one easy version of the story. Proxima B would then be telling us that biology can operate under far stranger conditions than Earth-based intuition prepared us for. But the pessimistic ending is not comforting either. Suppose Proxima B turns out to be dry, badly irradiated, stripped of most or all of its atmosphere, and maybe even chemically misleading. Suppose the nearest rocky planet in the habitable zone of the nearest star has already failed the test. That would matter far beyond this one world. It would make the case much stronger that habitability around red dwarfs is a lot harder than the phrase "most common stars in the galaxy" makes it sound. The closest serious example would stop being a promise and start being a warning. And that would be a harsh lesson, because red dwarfs are everywhere. They dominate the galaxy by number. So for years, one hopeful implication has been that if these stars are common, then potentially habitable planets around them might also be common. But if Proxima B, the closest and most studied serious case, turns out to be a dead end, then the easiest optimism starts breaking down. The nearest promising rocky world would be telling us that many of the galaxy's apparent opportunities may come with built-in failure modes. The closest example would become less like a doorway and more like a caution sign. But the most unsettling possibility is in the middle, because that is where Proxima B has been pointing for most of this story. Not a global ocean world, not a sterile rock. Something in between, a narrow refuge instead of a broad paradise. A buried ocean under ice, a salty dayside patch, a thin band near the terminator where conditions become barely survivable. A biosphere made of microbes, sparse enough or hidden enough that it does not announce itself clearly to us. That may be the most frightening version because it says life may often survive only in reduced and difficult forms. That is a much darker picture of the universe. Not empty, but not generous either. Not full of easy Earth copies waiting under every red dwarf. Instead, a universe where life squeezes into the margins when it can, survives in protected niches, and often remains hard to detect. The cosmos in that picture is not welcoming. It is barely permissive. Life does not flourish because conditions are kind. It persists because conditions are not quite bad enough to erase it completely. That is why the title lands when you frame it correctly. There might be life on Proxima B, and its terrifying is not about monsters, invasions, or anything childish like that. It works because every serious outcome is uncomfortable. If life can exist there, then life is stranger, tougher, and less dependent on Earth-like comfort than we thought. If life cannot exist there, then even the nearest promising world can still fail in ways that matter for a huge fraction of the galaxy. And if the truth sits in the middle, then life may be common only in forms that are cryptic, reduced, and almost spectrally invisible. That destroys the lazy middle ground people often fall into. The habitable zone is not automatically hopeful. A nearby rocky planet is not automatically promising. A biosignature is not automatically trustworthy. Proxima B keeps breaking those easy assumptions one by one. It forces every part of the argument to become more careful and more demanding. And that is the final reason this planet feels so intense. It may be the place that forces us to redefine several ideas at once. Not just life, but habitability. Not just habitability, but biosignatures. Not just biosignatures, but what counts as optimism in the search for life. Proxima B sits at the edge of several very different possibilities, and none of them are simple. It could be a battered but living world. It could be a dead world carrying false signs of hope. It could be a hidden world where life survives below the level our instruments can easily read. That is the real ending. The nearest exoplanet that might hold life may also be the planet that forces us to grow up about the search itself. It may show us that life can survive under conditions we once thought were too extreme. Or it may show us that even the best-looking nearby targets can fail. Or it may show us something worse for observers. A world where life survives in ways that make proof painfully hard. And that is why Proxima B is terrifying in the only way that really matters. Not because it is far away. Not because it is dramatic in a movie sense. Because it is next door. Because it is real. And because whichever answer it gives us may change what we think the universe allows. This video is for educational or entertainment purposes only. and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.